Okay, so let's go over to number 24 in our textbook, and we want to find the antiderivative big F of little f that satisfies the given condition. And then we can check our answer. They said by comparing the graph, but we can check our answer by, taking the derivative of big F. Okay, so the given conditions, we're going to find the antiderivative. Not the general antiderivative, but one antiderivative with these conditions. Little f is equal to 4 minus 3 times 1 plus x squared, the negative 1, given f of 1 is equal to 0. Okay, so that's going to give us a unique antiderivative. So let's see what happens. So first of all, this negative 1, remember we can't use our power rule when n is negative 1. So that's just kind of signaling to me to kind of clean this up a little bit. So I'm going to send that 1 plus x squared downstairs. And now I actually recognize this as a function as the derivative of a function. If it helps, I'm going to pull that 3 out. Maybe you could see it a little bit clearer. Okay, but anywho, let's start taking the general antiderivative. All right, so we need we need a function whose derivative is 4. Well, the derivative of 4x is 4. So there you go. And now we're going to think of a function whose derivative is 1 over 1 plus x squared. And that is the inverse tangent. So really important to know our derivatives, right? Or else it'll be really hard to figure out the antiderivative. Okay, and again, that's because the derivative of the inverse tangent is 1 over 1 plus x squared. And then to make it general, we're going to do a plus c. All right, and now we're going to figure out that c, since f of 1 is equal to 0. So let's see what happens. Let's plug in x equals 1. So 4 times 1 minus 3 inverse tangent of 1 plus c equals 0. All right, so we have to think now, inverse tangent. So what angle? So this is really saying tangent of what x is equal to 1. All right, well that happens when the sine and the cosine are the same. That's pi over 4. All right, so the inverse tangent of 1 is pi over 4. Okay, so that's that. Little substitution. And then plus c equals 0. So now we can solve for c, right? We have one equation and one unknown. So how we can do that, let's subtract 4. Let's add 3 pi over 4. So we're solving for c, right? So we added 3 pi over 4, we subtracted 4, and that's your constant. And so now we're ready to state our answer. The antiderivative that satisfies those two conditions is 4x minus 3 inverse tangent of x plus this crazy constant, 3 pi over 4 minus 4. And that big thing is your solution. All right, so let's look at another example like that. This time we're going to start with the double derivative, and we're going to be told the double derivative is 8x cubed plus 5. We have these conditions, f of 1 equals 0, f prime of 1 equals 8, and now we're going to find f of x. We're going to find that original parent function, okay? Well, we're going to have to take the antiderivative twice, okay? So if f double prime is this, that gives us enough information to go one level up. So we used to call it capital F, but if it's the double derivative, we can just go up to the single derivative. Okay, so we have to think what function has this derivative, 8x cubed? Well, and you might be able to do some of this in your head, depending on how much mental math you do. Add 1 to the exponent, and then divide it 1 over that new exponent, okay? And then the antiderivative of 5 is 5x. And then we have to add, here, make sure it looks like a single, good. Then let's add a c, all right? So we're looking at, let's see, 8 divided by 4 is 2, x to the 4th plus 5x plus c. And we can always check our work. Notice if we were to take this derivative, it would be 8x cubed plus 5 plus 0. 8x cubed plus 5 plus none, okay? So we know we're on the right track, right? And again, that's f prime of x. Okay, so before we take the antiderivative to get to f, we have to figure out this constant c. And we're going to use this piece of information. F prime of 1, I love plugging in ones sometimes. At least in polynomials, I like plugging in ones. We know f of 1 is equal to 8. All right, so we have 2 plus 5 is 7 plus c equals 8. We'll solve that for c. 2 plus 5 plus 1 is 8. So c is going to be equal to 1. So f prime of x, the derivative of f, is 2x to the 4th plus 5x plus c, but we just said that c is 1. So that's our function. Okay, so remember we want to find f of x. So we're going to take the antiderivative of f prime of x, or again, we're going the opposite direction. So rinse, wash, and repeat. The new exponent is going to be 4 plus 1. Coefficient will be 1 over 5. And now the antiderivative of x is going to be x squared, and the coefficient is 1/2. All right, and then what's the antiderivative of 1? It's 1x. And then now we have our plus c. All right, so f of x then, we're almost there, right? It's going to be 2/5 x to the 5th plus 5/2 x squared plus x plus c. And remember, we can always check by taking the derivative of f of x and making sure we get back to f prime. All right, and then the last piece of information we have is that f of 1 is equal to 0. So let's use that. F of 1, so it'll be 2/5 plus 5/2 plus 1 plus c equals 0. Okay, so we have to add 2/5 plus 5/2 plus 1 plus c equals 0. So I'm just going to give everything the common denominator. That common denominator is 10. All right, so 2/5 multiply top and bottom by 2. 5/2 multiply top and bottom by 5. And then 1 multiply top and bottom by 10, okay? So 4 plus 25 is 29, plus 10 is 39/10, plus c equals 0. So c has to be negative 39/10. All right, and then that is going to get us our f. This is what we were trying to find. They wanted us to find f. And so f of x is equal to 2/5 x to the 5th plus 5/2 x squared plus x minus 39 over 10. That was that c. So this is the final solution. That one's the final solution. All right. So kind of on the same note, so in other words, starting with a double derivative, and then finding the single derivative and then finding our function, we're going to do the same thing with our position function, our velocity function, and our acceleration function. All right, so for instance, we're going to be able to find the position function just given the acceleration function. Okay, because we know that we have all of these relationships. We know that s of t, if we take that derivative, we're going to get, the velocity, the rate of change of the velocity. And then if we take that derivative, we can get the acceleration. All right, so I'm sorry, when I say find the position, oh yeah, so now we're going to start here and we're going to work our way up. Okay, where previously we always started with the position, we took the derivative, we found the derivative to get us down to the acceleration. Now we can go backwards. We can start here and do two antiderivatives to give us the position. Okay, so that's the kind of things we're going to be doing next. So let's go over to number 62. And we have that a particle is moving given by s. We're going to find the position of the particle. Okay, so the position is s. So we're going to find s of t. All right, and for number 62, we're given that the acceleration function is 3 cosine t minus 2 sine t. And we're told that the position, the initial position is 0, and the initial velocity is 4. Okay, so that's our problem. All right, well, to find the velocity, that's the antiderivative, right? So remember, the derivative of the velocity is the acceleration. So we have to think the derivative of what gets us cosine? Well, the derivative of sine gets us cosine. All right, and then the derivative of what? Look, we can think of this as a minus sine. What function gives us derivative negative sine? Positive cosine. So we can think of that as plus 2 cosine t, right? And then what are we missing? The plus c. So now it's time to figure out the c. And we know that the initial velocity is 4. So let's plug in t equals 0. And we know that has to equal 4. All right, so sine of 0 is 0. Cosine 0 is 1. 2 times 1 is 2. So 2 plus c equals 4. That means c has to be, here, I'll write that 2. C has to be 2. All right, so then our velocity function is 3 sine t plus 2 cosine t. And now instead of plus c, it's going to be plus 2. All right, so now that we have the velocity function, we can take the antiderivative to give us the position function. All right, and that's because s prime of t is equal to the velocity. So we're taking the antiderivative. All right, so we have to think, what function has derivative of sine? And it's positive sine, all right? Well, cosine is negative sine. So if our derivative is positive, it was probably negative to begin with. All right, now when we take the derivative, it'll be negative sine, positive sine. All right, so what function has derivative cosine? It's sine. What's the antiderivative of 2? It's 2t, because the derivative of 2t is 2. And then we need the constant plus c. All right, remember we can always check by taking the derivative to making sure we get back to the velocity. All right, well, what do we know? We know initial position is 0. So let's plug in a 0. Okay, let's see. Cosine 0 is 1, so we're going to be negative 3 times 1 plus 0 plus c equals 0. Solving for c, we get 3. And we have our position function. So same as before, negative 3 cosine t plus 2 sine t plus 2t plus c, but that just became 3. And then that's your solution, just finding the antiderivative. All right, and we have one or a couple more examples, but they're going to be word problems using position, velocity, and acceleration, and we'll do that in part 3 of our video.